6.69. A box is sliding with a speed of 4.5 meters per second on a horizontal surface. I'll draw the surface first. Here's the box. And when at point P, it encounters a rough section, the coefficient of friction there is not constant. It starts at point 1 at P and increases linearly with distance past P, reaching a value of 0.6 at 12.5 meters past point P. So, say P is at x equals 0, and then over here this is x equals 12.5. And mu is 0.100 at point P, but over here mu equals 0.600. So this box is sliding in with a velocity of 4.5 meters per second. Once it reaches this point, it encounters some kinetic friction. So it's going at constant velocity, hits this point, and then starts to slow down. And then at some point it stops. So I'll just keep it up there for now, in case I need to grab it again. It's got an initial velocity of 4.5 meters per second. We are looking for the point at which the box stops. So let's just pick a point. We're going to call that capital X, as opposed to little x. Notice I make my little x's a little bit fancy. Capital X's, I'm just going to make a big bold X. So where the box stops. These numbers, these distances, are given so that we can figure out how u changes with x. So mu is a function of x. We know that mu at x equals 0 is 0.100, too many zeros. We know mu at 12.5 is 0.600, and we know that mu changes linearly. So we just have to figure out the linear equation. Mu as a function of x is going to be, like a mu naught plus a slope times x. So the slope is, what is the rise? The rise in the coefficient is the difference, right? And divided by the run, 12.5 minus 0. So that's I think let me just double check. 0.6 minus 0.1, I should have known that, divided by 12.5, 0.04. Yep. So that's the slope. Mu naught is just 0.01. So this function, mu as a function of x, is 0.100 plus 0.040 times x. I'm going to put a bold line here just to remind myself that that's an important equation on that line. Let's see. So the next thing we got to do is we got to know that the total work done on the box will be equal to the change in the kinetic energy. So we know that the box starts off with an initial velocity, so therefore it has an initial energy. And you might ask, well, kinetic energy is 1/2 mv squared. Right? So the change in kinetic energy is 1/2 mvf squared minus 1/2 mv naught squared. And we don't know m. Well, I think a lot of students have trouble with this approach. Okay, we don't know m, so therefore we don't know what delta k e is. But so what? Just go with it. The final velocity we want to be 0. So that's 0 because we want to know the change in the kinetic energy where the final velocity is 0 because it stops, and v naught will be the 4.50 meters per second. But I kind of don't want to, I don't like to write numbers, and I think a lot of students also have trouble with this because I think they forget that these are just shorthand, some of them. So v naught is shorthand for 4.50 meters per second, and then they eventually kind of forget what they know and forget what they're looking for, yada yada yada. Just don't, it's okay. Just it's a pronoun, right? You can say John is the best recitation teacher because he cares for his students, right? He is just a relabel of my name, John. He is just a relabel, just like v naught is a relabeling of the number or the velocity, sorry, the speed 4.5 meters per second. Anyway, hopefully that didn't confuse anyone. So what we have here, at least on the right-hand side, is negative m/2 v naught squared. The left-hand side. All right, I don't know my left from my rights. I got to think about them. So I think I said the right-hand side. So now the left-hand side, what is this work total? The work total is done by the total force. And what is the total force? Well, what is the force? What are the forces acting on this box? So this dot here represents the box. There's a normal force acting on the box. The box has its own weight. And then there's a friction force, kinetic friction force, lowercase fk. I'm not using an iPad, I'm using a cheap Samsung tablet. And the aim is off with the pen. The normal force and the weight, they balance out such that the total force acting on the box is going to be negative fk I hat plus 0 j hat. if this wasn't 0, then there would be a net force, at least a component of the net force in the y direction, and therefore the box would fly upwards or sink downwards. But I mean, we don't want that to happen. This thing just stays on the surface. Its acceleration or deceleration is only in the horizontal or x direction. However, we know that Fk, the friction forces, are always a kinetic coefficient. We're just talking about kinetic friction, so I'm going to leave the k off of this, of the mu, times the normal force. So, let's go back down here. The work done, the total work done, is due to the total force. But in this case, that total force is x dependent, depends on x. So I'm going to put that there. And therefore, I can't just multiply by a distance. I have to use a differential displacement here. And what are the limits of integration? Well, I need this to be changing kinetic energy. The limit here, the lower limit and the upper limit, correspond to these two terms, these two kinetic energies. Like a kinetic energy final minus kinetic energy initial. So, and one more thing before I get onto this. This differential L, this line integral, in the present case is just I hat dx. Right? This is a little displacement in the x direction. This is a vector, so displacement in the I hat direction. So I'm going to replace this with I hat dx. Okay, so the lower limit here corresponds to when I have the initial kinetic energy. And then the upper limit here corresponds to where or when I have the final kinetic energy. That final kinetic energy, 0, is when the velocity is 0. And my definition of what capital X was where the box eventually stops. So Vf equals 0 when x equals capital X. So the upper limit on this integral is capital X. Okay. So, let's start putting the pieces together. Little x equals 0 and little x equals capital X. This I don't know yet. I don't know what this capital X is. F total is just due to the kinetic friction minus mu n, and n has to be equal to the weight, because those two forces in the vertical direction balance. So that was negative mu of x times n for the total force, and that's all in the x direction, dotted with I hat dx. So that's equal to negative mg, that's the w, 0 to capital X of mu of x dx. So I dot I just became 1. And that integral on the left-hand side is equal to 0, because that's the kinetic energy final, minus 1/2 m v naught squared. Alright. It's getting exciting. Okay. 0 to capital X. Oh, now I'm realizing well, no, it's fine. I got a little scared because I have a mass here, but I also used an m as my slope here, but we don't need this anymore. Right, this was the slope for mu of x. I guess I tried to make it, this m is way more scripty, way more italicized than this m, the mass m. See this? These are the things that keep me up at night, these kinds of problems. So that's my mu of x, integrating that in x. And I'll just leave this stuff up here for now and just carry on with the quote left-hand side, and then I'll tack this on at the end. Oh, but by the way, you can see that this mass cancels with this mass. So I never really needed to know it. I never did need to know it. So you got to be suspicious when the problem doesn't give you a quantity that you think you might need. It might be for a reason. It might be because something cancels out. Okay, so what is the antiderivative of this in the brackets? 0.100 x plus 0.040 x squared over 2. And I gotta evaluate this at capital X, 0. This one's easy, right? If I put x in there, that's all 0. So I get a negative mg equaling negative m over 2 v naught squared. Now I'll cancel the m's from both sides here. Cancel the signs. This becomes, so I'll use arrows and not equal signs. If I put equals, it would be wrong because I canceled an m, and then that stuff wouldn't be equal to this stuff up here. So I get a g 0.100 capital X plus 0.02. I'm gonna divide out a 2, capital X squared. And for those who want to see it, so x of the brackets at x minus the brackets at 0. That's all equal to v naught squared over 2. Oh, and now I see that since I'm looking for what x is, and I know v naught squared and I know g, looks like I'm going to have to solve a quadratic, which is always fun. Let's see here. I'm going to divide out a g on both sides. Then I get 0.02 x squared plus 0.100 x. Probably should have put a 0 here, just for consistency. and then v naught squared over 2g equals 0. So x is equal to negative 0.100 plus or minus square root 0.100 squared minus 4 a 0.020 c is negative, what was v naught? Put in the number. Let me go ahead and take care of those signs. 4.5. That's 4.5 squared divided by 2 times 9.8. All over 2 times 0.020. Oh boy. Okay, 4.5 squared divided by 2 divided by 9.8 times 0.02 times 4 plus 0.1 squared equals square root of that, save. So I'll subtract 0.1 from that, divided by 2 divided by 0.02, I get 5.1097, carrying out a little bit extra significant figures just in case. Now I've got the square root saved already, so just 0.1 negative minus recall divided by 2 divided by 0.02. The other solution is negative 10.1097. Alright, so this is obviously, I mean, it's mathematically correct. What does it correspond to? Let's see, what does that correspond to? For negative x, so for x in this region, stuff to the left of x equals 0, mu can become a negative. I mean, I guess it's not exactly to the left of x equals 0, but so at some point not too far away from x equals 0. There's a point where mu becomes negative. Mu of x becomes negative for all x to the left of some line. And in our formula for the total force, we're going to get a positive, so we get a positive force so you know what, I actually don't know. I don't want to think about it. The point is, the box was moving to the right with a velocity of 4.5, so it's going to have a positive value of x at some point. I mean, it's going to have positive values of x until it stops. It's not going to go backwards and then go into negative x's. So mathematically, something worked out so that this is mathematically correct, but physically, this must be the right answer. So the correct answer is x 5.11 meters. Is there another part to this problem? What is the coefficient of friction at the stopping point? Easy. So the function for the coefficient is mu of x is equal to 0.100 plus 0.040x. So mu at 5.11 meters, well, I don't need the meters, 5.11 is equal to 0.100 plus 0.040 times 5.11. 5.11 times 0.04 plus 0.3044 is the coefficient. Part B. How far would the box have slid if the friction coefficient didn't increase but instead had the constant value of 0.1? Well, if that were the case, then the work total would be negative 0.100 times mg times, I'll call it L. So now the box started here, ended here. The change in the kinetic energy will still be the same. It'll still be negative m over 2 v naught squared, with the final velocity was 0, so that was 0 here. And we again get a minus m to cancel. So we have L being v naught squared over 2g all divided by 0.1. It's 4.5 squared divided by 2 times 9.8 times 0.1. Forget the sig figs there. 4.5 squared divided by 2 divided by 9.8 divided by 0.1. And I get 10.332 meters. So L is 10.3 meters. Easy peasy.